So I want to just backtrack for a second and talk about some stuff that I saw on the homework. So I was just getting up all of your graded homeworks just prior to class start. So grades on homework 3 are up, solutions are up, and my comments are there too. Um, just one thing I just want to be sure is that I'm not grading anything on a personal level. These are all just constructive feedbacks. I love you all. And so it's nothing personal. They're just kind of comments to try and help you improve your proof writing. So, I try not to be very blunt, but if you take things that way, that's not my intention. So hopefully you take my comments as constructive criticism. Even if you were getting, top grades on your proofs, I very well may have left some comments, maybe a lot of comments. So please do heed those things. Even if you're getting them right, I think everybody's got some room to improve. But I want to comment on a couple of general things that I did see on a number of homework. So this was question 7 from homework 3, which was, okay, we've got some sets. Prove if A is a subset of B, then A intersects C is a subset of B intersects C. And so just kind of one thing, when we're doing this proof, some people kind of went about it like something like this, let X be in A intersect C. Then we know that X is in A and X is in C. Since X is in A, we know X is in B. Because A is a subset of B. So this is what more or less some people had some line of argument like this. And so the comment that you might have seen on your assignment is we don't know that, right? Until just now. So when we're proving a conditional statement like this one over here, the very first thing to do, you don't have to do this, but a good way to avoid kind of losing a reader like, well, why did I know that, is to just state right away, suppose A is a subset of B, because that's the hypothesis of this statement that we're trying to prove. So the very first thing that you can do is state this hypothesis, and we don't need to justify that, right? That's pretty much the only thing that we're allowed to assume. And now when I'm reading the proof and I get to a part like this, I could say, yes, I do know that because you told me that we are assuming that. But without seeing this assumption, then I really don't know that A is a subset of B. So just be sure to not forget to include that detail. It's just a really subtle thing. And kind of the other thing that I observed, well, a couple of things. Another thing that I observed in these proofs, so let me just stop. Any questions about that comment? Another thing, just to kind of see a different approach that some people had, they started off okay, and then they kind of knew that the general idea is, well, A is contained in B, so anything in A intersects C should contain something in B intersects C. And I could kind of see where the logic was going, and you kind of had the general idea, but you left a little bit of it up to the imagination for the reader, for me. And so when you're doing subset proofs, there's always a blueprint that you can stick to. And the more that you're able to stick to that blueprint, I'm not saying you have to do it, the easier it's going to be for the reader to follow. So kind of with subset, proving one thing is a subset of another, these proofs generally start with let X be in the set over here. And then you want to show that X is in here. So if it helps you, you can kind of just stick that blueprint in and see how it gets there. And then this avoids any ambiguities of saying like, well, any element in here should be in there. It's really nice when we have like a concrete element that we call X that we can all refer to. Relating to this, in some of these proofs, I saw a lot of people somewhere along the way claiming that X is an integer or something like this. And we don't know that X is an integer, and it's not really relevant to this proof. So just keep in mind that in general, unless we're specifically told that the set contains numbers or integers or whatever, we should just refer to them as elements and not assume that they're numbers or integers. They could be functions, they could be sets, they could be, sets could contain sets of colors or days of the week. So these could be more abstract things. So just, we're used to dealing with numbers, but unless we're told what the set, what the elements of the sets are, we shouldn't assume it. And in fact, it doesn't really matter to this proof what those things are. Any questions, comments? Yeah, so I'm not too concerned about this, but it does just kind of read a little bit weird when we throw in some things that aren't needed. Yeah. So those were just a couple comments there, and that if you are getting stuck, you can try and fall back to these blueprints that we've been talking about. And maybe you don't like them and you want to do it another way, that's fine. But I think it might be good to try and think about this general method before kind of ad-libbing. Okay, then, oh, this is not the homework. Then there was an last question on the homework, question 9, and then we'll get back into proof by contradiction today. So let's see, question 9 said, basically we want to show that M minus this is equal to this. And so here again is just like a really nitpicky thing, but that's what I'm here to do. So I'm sorry if you felt that my comments were nitpicky, but I think that's the only way your proofs get better, right? Is if someone points out little areas where you can improve. For a proof like this, I think most people were correct in that, okay, I know that there's actually 2 things that I need to prove here. And so what I saw in some people were people referring to these things as cases. And I'll just say, like, we use things pretty, pretty sticklers for how we use terms and notation in mathematics. And so when we're using cases, you should really think this as more of like, I'm going to prove this one statement using different cases. In this sense, we're not really doing cases. We're proving 2 directions of a proof. So, these subtle things, it just might help to, rather than call these things a case, it does help to tell the reader that we're doing things in different stages. So in that sense, it is steps, but we're really just proving one, we're proving the first set is a subset of a second, and then it's not a different case, right? But it's an entirely different proof that we're doing over here. And so, just a way that you could state that more clearly would be using this. So you really want to stick to cases when we're using them in that strict sense. That's a really subtle thing, but nice to point out, since I did see this happen on a number of homeworks. And then for a lot of you, you probably got some comments in your homework. You might not have had a chance to go through them that say like, hey, can you give me more details at this spot or at that spot? And so sometimes that might be ambiguous. So I tried to clear up like what I mean by this would have been enough detail. And so these proofs were examples of that. So this proof, again, since it's a subset proof, we would start with this, right? And then ultimately what we're trying to show is that it's in here. And when you're making your arguments, like the sentence that I say right now should be a direct result of only what came right before this. And so I don't want to do too many jumps in logic in one sentence. So what I saw some people say is, okay, well, let X be in here. Well, then X is in M and X is not in N, or X is not in P. So therefore this. And that's not enough detail in a proof like this. I would need to know, like, you should just assume that the reader is really not trying to think at all, right? I'm just on cruise control and I'm trying to just make sure that your statement comes directly from the previous thing that came before there. So if you're not sure how much detail you need to put in, I think it's better to err on the side of adding more detail. That really convinces me that you understand how everything was flowing. So in this case, like what I wrote down here doesn't follow directly from what we are assuming here. So you really want to think about, if X is in there, what's the next thing I can say? And just take it step by step. And this might actually help you miss any gaps in your proof. So if I know X is in there, then I know it's in M, and by definition of set difference, right? That's all I can say directly from that previous sentence. And then just take it step by step. Okay, so now I know that X is in M and it's not in N intersect P. And kind of one error that I did see in some people is they put an and there as opposed to an or. So just watch out for that. But now you can see that, like, we're just taking things step by step by step and not really glancing over any detail. So this is really coming from the definition of set difference. This is coming from definition of, basically De Morgan's law. What it means to not be in the intersection means that it's not in the union of the complements. And now we can see that it's in M and it's not in N, or it's not in P. So there were a couple of justifications that you would need to do before getting to that point. Okay, any other questions? So I would definitely encourage you to go back and look over my comments. If you don't agree with them, or possibly I misunderstood you, you're welcome to let me know, to take another look at it. But try and rewrite them. And I think that we're definitely making some improvements here. So the goal is, by the time the exam comes around, we're getting our proofs up to standards here. So otherwise, I'd say the comments were a little bit more individual. So I'm happy to kind of talk about any individual comments in office hours. Lindsay and I can help you with that. Okay, any other questions? Okay, so yeah, overall things are looking really great. So I'm really happy with the proofs that you guys are writing. I think the things I'm finding are very correctable, easy things to improve. So that's good. Okay, so otherwise, you didn't have a quiz for today. We're just going to keep talking more about contradiction. For Monday, I'll get it up tomorrow. There will be a quiz on, so we'll be moving on to some material with dealing with functions, one-to-one functions. We'll do some proofs with that. And then you've got a homework assignment that is due on Monday as well. Okay, and don't forget there's a survey up online as well. And so if you get, I haven't checked the response rate on that. I'll check after class. As long as we get enough people responding, then you'll get some bonus points for the first exam. Okay, so yeah, let's just keep on working with proof by contradiction. And so, right, in this process, it's really important to be able to negate statements correctly, because basically proof by contradiction means we're going to try and show that the negation of the original statement in some sense is wrong. That leads to some contradiction. So let's see, last time, this is homework. Last time we did one together, we did two together, and then I think everybody worked on three, some combination of that, right? I think we did, here's one, maybe we did one together. Maybe we didn't do this at all. This might be last year's solutions. Let's see. I don't think we did 4, did we? Or 5? Nope. Okay, here's this year's. Nope, contrapositive, sorry. Okay, here's what we did last time. So let's see, we did question 1, talked about different ways that we can do it. Yes, this looks more familiar. And we did question 3 in groups. Yeah, okay. And so I think we're pretty much up to this one over here. So I definitely want to kind of do a couple together and then give you a chance to do a couple together. Yeah, so let's take a look at question 4. We can try this one, and then we'll shift things over to you guys to try and work on the last couple ones. Okay, so okay, we want to prove there is no smallest real number. And again, we can't really do direct proof here or contrapositive proof because this is not a conditional statement, right? This is a statement about non-existence of something. So here we just have one statement, P. So the idea with proof by contradiction is that we are going to suppose not P and hopefully find the contradiction. And that's kind of the tricky part about proof by contradiction, again, is that like the goal is a little bit more vague here. In some sense, that's good. Any contradiction will do, but we don't have like a concrete goal necessarily. So in this case, a good first step would be to state the negation of this statement. So if the statement is there is no smallest real number, what would a negation of that statement be? There exists the smallest real number. That's right. So so these proofs by contradiction start by supposing the opposite, the negation, I should say, of the original statement. I'm going to call that smallest real number x. Now, again, the goal is to get a contradiction. And when see a way that we can contradict that x is the smallest real number.
X minus R is smaller than X.
Yeah, so X minus R, what's R? That's all I'll ask.
Another real number.
another real number as long as it's positive, right? If we're subtracting it, yeah. So that's right. So we can say, so we can consider something like, we could pick R and plug it in there to make it a little bit more general. We could pick a favorite number, R, right? And for example, 1 would do the trick. So let's consider y minus 1. Okay, y is less than x, so therefore x is not the smallest real number. And that's all we would want. That's all we would need to show for that one. So here's a case where, proof by contradiction, we can get a contradiction really, really quickly in that sense. Any questions? So this is kind of similar to like the square root of 2 problem that we had to show that square root of 2 is irrational. That was not an if-then statement. So all we could do was start by assuming the opposite, that it's rational, and then spin around and try and get some contradiction. Here, the contradiction we could get was pretty quick. Good.
Hey, Adam, can I ask you a question?
Yeah, I'm just internally debating which one of these I want to do. Feel free to interrupt. Yeah.
For number 4,
Yeah.
I see that you put y is equal to x minus 1. Can you like have made it any other arbitrary number? Or?
Yeah, you could. So yeah, like Mitchell's suggestion was to say this, and if you do that, then you just need to say for r, bigger than 0, and that would work too.
Cool. Sweet.
Yeah. Yeah, so I picked 1. That's my favorite number. I'm boring, but you could pick 2, 3, 4, 5, or R. Yeah. Okay, so let's see. 7 is definitely going to be a long proof. So maybe that's not the best one to start with. 6 and 7, 5 and 6 are pretty similar. So we'll do 5. And then I'll have you guys work on 6 in a second. That did not work. Okay, so here is 5. We want to show that any even integer cannot be written as the sum of 3 integers, an odd number of which are odd. That's a big statement there. So basically what we're saying is if we have an even integer, we want to write it as a sum of 3 integers, then we can only have either 1 or 3 of them be odd, is essentially what that is saying. And again, this is not a conditional statement, so really contradiction is the main way that we can go about thinking about this. I guess you could think about it, if x is even, then it can't be written as, or it can be written as a sum of these 3 numbers. Okay. So let's see. Any thoughts about where we could get started on this one? So I wrote this as a conditional, right? Rewrote this as a conditional statement. This is really saying if we have an even integer, then here's some conclusion. So what would the negation of that statement be? So there was a suggestion here that can we suppose A, B, and C are odd numbers? Yeah, so we'll need to get into something like that with A, B, and C. That's right. But when we're doing this proof by contradiction, right, these proofs usually start with us supposing something, telling the reader, here's what we're going to assume.
So if it's a conditional, the negation would be P and not Q.
It would be P and not Q. That's right. So we're going to assume X is even, and this conclusion, in fact, is wrong. So in other words, it can be written in this way. That's right. And so when we're doing this, again, definitely good to get in the habit of telling the reader, here's how I'm going to prove this statement. Here's my proof technique. And then let's say, well, using this proof technique, here's how my proof is going to begin with me assuming the negation of the original statement, which is X is even. And, right, it can, since we're going to do the negation of that, be written as a sum of three integers
So would you need to have two cases, one for one of the A, B, or C being odd and one for three?
Yeah, that seems like a great idea. Yeah, so that's right. So now we're going to need to try and get some contradiction. And so the idea here is, okay, we've got three integers that we're going to write X as a sum of, and this is saying that we can do it as long as we have an odd number of which are odd. So let's kind of take each of those cases, that's right, where one of them is odd or all three of them are odd, and show that in any of those cases, we get some contradiction. That's right. That's a great idea. And it's possible when we go through these cases, we might see that like, hey, these were done the same way. Do we really need separate cases? Or we might see that these really were, required some different logic. So in my mind, I think this makes sense as well. So there's one case which is X is equal to A, B plus C. Where those are all odd, so that would be three odd integers. And then just to give myself some room, okay, and the second one is going to be where one of them is odd. And whether I choose A or B or C to be odd, right, doesn't really matter. And hopefully you guys can agree that like when I go through this proof in case 2 with A odd, B and C even, it wouldn't have effect to proof if instead I said C was odd and A and B were even. But before we go any further, does it make sense where these cases came from? And that would be it, right? So otherwise, if an even number of them were odd, that's not really part of this statement. So we're not concerned about that situation. Okay, so let's take a look at case 1. If all three of them are odd, what might be a good way to start this one off?
You could plug in 2n plus 1, right?
Yeah, so then we can say, right, let's suppose A, B, and C are odd, which means A is equal to 2k plus 1, B is equal to 2n plus 1, and C is equal to 2m plus 1. For some integers k, m, and n. Which makes sense. Okay? That's the one thing that we suppose. So let's kind of, our next sentence should be like, well, if I assume they're odd, what can I say about them? Then what seems like a reasonable thing to try next?
Plug them in for A, B, and C.
Then we can plug them in. Okay, so then we have and then what seems like a reasonable next step after that? So kind of, what do you think the goal is where we're heading with this proof right now in this first case? What am I hoping to show, do you think?
Combine them and factor to prove that the right side is actually odd.
Yeah, so we're going to try and show that the x is actually odd, right? And that would give us a contradiction here since we assumed that x was even. That's right. And so what can we do with this sum to try and show that, just to use some additional letters here, we're running out of letters, right? We want to show that this is odd. So we'd like to show that it can be written as 2 times an integer plus 1. How can I do that? What's the integer that we would need there?
3a plus 1. I'm sorry, 3.
Right, so I want to rewrite this sum in this way. So what goes in here? I'm done. So I'm going to leave it up for you guys to do the algebra here. Okay, thank you. Yes, so let's see. We can pull out a 2 and we get k plus n plus m plus 3. And we actually want a plus. Yeah, that's right. So then we can write 3 as yeah, I think we're getting the right idea here. Maybe we've got a chat window here. I'm trying to follow along in the chat. So I want a plus 1 on the end. So how can I break this up so I have 2?
So you could do a k plus n plus m plus 1 inside the parentheses.
Yeah, I think that would do it.
Yep.
And again, you know, whether you need to show like all of the intermediate steps of this algebra, I think it's fair to go from here straight to here. I don't need to see all of the intermediate stuff, but it might be helpful for you to write it out. But we do need to be particular in that we get this in the form of 2 times an integer plus 1. Having it as 2 times something plus 3 technically doesn't fit the definition of what it means to be odd. So we can probably figure that out. Okay, so this tells us that x is equal to 2p plus 1, where p is this k plus n plus m plus 1, which is an integer. So that leads us to a contradiction. So case one can't happen. So the only other possibility then is like, okay, well, it's still possible that there can be an odd number of odd things. What about if just one of them is odd? So let me just stop here. Any questions about this first case, why that was a stopping point and we don't have to go any further with that one? Okay, so what do you think we can do with this second case?
Define A, B, and C, and one as being odd and the other two as even.
Yeah, so let's let A, B, C, right? So we can do the same sort of thing now. And this is why it's nice that we just like concretely chose. I'm gonna select this one to be odd and the other ones to be even so that we can fill these in. And in fact, which one I decide to be even versus odd isn't going to affect our proof. So maybe in a case like this, here might be a nice way to say this. There's nothing wrong with what I had up there, but just to kind of see some terminology that gets used in proofs sometime. So here we're assuming that exactly one of A, B, and C are odd. And so without loss of generality, we can suppose A is odd. And whether we picked another one to be odd wouldn't affect this proof. So that's why we can say without loss of generality, the fact that I picked A to be odd isn't going to affect the general situation, since the proof would follow the same way if we picked B to be odd or if we picked C to be odd. So this just might stop a reader from saying like, well, why did you pick A to be odd? Why not B or C? And then they see this and they say like, okay, I realize it wouldn't have mattered which one we picked to be odd. Okay, now we can define the structure, the form of what these integers would have to look like. Okay, and just like notice as you're going through your proofs and you're talking about it with your classmates, you know, just kind of do some checks with each other to make sure like, does the sentence I'm about to write, does that follow pretty immediately from the previous thing? Or are we missing something in between? So now this A plus B plus C would be 2K plus 1 is A plus B plus C. And what do you think would be a convenient way to write this out to get to our contradiction?
Just factor out the 2, so you could have 2 times K plus M plus N, and then there'd be a 1 after that.
Yep, so we don't have to be as fancy here. Yeah, and so here the cases were needed because these proofs did follow a little bit differently. And so I don't think we could have done both of these together at once necessarily. And that do it. So that's a good way of using cases there. And notice like the way that I use case 1 and case 2 here is different than, you know, when we're proving set equality, when we have 2 parts of that proof. We're not doing cases. We're kind of showing here's the first part of the proof and here's the second part of the proof. Whereas here we are really just proving one thing, and that required us to break it down into 2 different cases. Yeah, so I'm getting some messages in directly to me and some going out to everybody. So you're welcome to message everybody or myself. I don't think there's been much going on. There's a little bit going on privately. So yeah, I mean, if you're messaging things, you're welcome to do it to me or to everybody. Just keep in mind, it's useful for everybody to see if you have a comment like, oh, I think the next step of the proof should be this. You're welcome to send it to everybody. If you're kind of a little bit shy about that, that's fine. Just direct message it to me and I'll try and repeat it to everybody else. But were there any comments or details that you guys have questions about here? Okay, so let's give you guys a chance to work on these in groups. So we're up to number 6, which is a question with parities, odd and even. So I don't know if you've defined this carefully, but I don't know why this wasn't highlighted. This is important too. But we say that 2 numbers have the same parity if they're both even or they're both odd, and they have different parity if one is even and the other is odd. So that helps maybe say things more concisely, since if I were to try and say a statement like 6, that's a little bit nicer to say they have the same parity as opposed to say if x and y are both odd, or if x and y are both even, then xy, you know, has the same even or oddness as the first thing, blah, blah, blah. So it's really nice to kind of use this parity idea here. And this might help us knock out cases at the same time. So here we have a conditional statement. So I just want to make sure before we break up into groups, we've got the right idea about how we could get started with that one. And when you're going in your breakout rooms, would be great, again, if you guys, you're awesome class in your breakout rooms, the way you guys are working with each other and using the whiteboard or whatever is really, really helpful. So that's great. So in this case, if you're looking for some structure as far as like, how can I get the first step of proof by contradiction, it would be noticing here that, okay, this is a conditional statement. And so here is statement P. Is that these 2 integers have the same parity. And then statement Q is x, y, their product has the same parity as x and y. We're going to try this proof by contradiction. And does anyone have a suggestion for how this proof might work? You're welcome to take the mic, chat it.
Suppose x and y have the same parity, then xy has a different parity than x.
Good. Yes, thank you, Mitchell. So that's right. So we're going to suppose that P is true, which is X and Y have the same parity. Okay, and now we have additionally assumed so there's a number of contradictions that we can reach here. But the first thing to note is, okay, does it make sense that like this is going to be our opening assumption, and then we're going to try and get some contradiction from this opening assumption here. And so some possible contradictions that you could get is like you could show that X and Y by going through some logic, see X and Y can't have the same parity, or the product XY has to have the same parity as X and Y. So we've assumed a number of things in this statement. All we need to try and do is contradict something in that statement. And so I'll leave that for you guys to think about, but at least that's the goal in this process. Somewhere along the way, by these assumptions, this is going to have to lead to some contradiction in logic. So I'll ask you guys to start thinking about that one. And if you get through that one, you feel happy and comfortable, everybody in the group is comfortable with that. Okay, then we've got number 7, which is a biconditional statement with sets. So there's a lot to unpack in that one. So start thinking about that one if you happen to get through 6, and then we can talk about 7 towards the end of class. Okay.
I have a question. Are you allowed to use explicit numbers to prove a contradiction?
Can
you set X and Y equal to a specific integer and then prove that it meets not Q or not P?
So for example, what do you have in mind here?
Well, I was actually looking at number 6.
Oh, I see. Yeah, that's what I'm talking about. So what did you have in mind in number 6?
Well, if you just set X and Y as 2 integers that are both divisible by 2, which is the definition of even parity.
So yeah, so let's pick some specific numbers and see how that would go. So like, let's say like X is 4 and Y is 6, they have the same parity. Then X times Y is 24. It also has the same parity. So I'll say like this in itself is not, oh, I see. Does it contradict this statement over here? So, I mean, the fact that we started with this statement seems like this doesn't necessarily contradict what's going on over here. This is saying, okay, it is possible for X, Y, and XY all to be even, but that doesn't necessarily contradict that it would also be possible to get something odd over here. So yeah, if you find like one counter example, that's enough for a proof. But if you show that like one example works, that's not enough to prove that like all such examples work. Yeah, so I think you're not too far off, and that there are situations where we can prove something by providing one counter example. This statement here seems to be a little bit more more general. Yeah. Yeah, so I would start to think about it. Yeah, there's some discussion going on about maybe we should use cases or something like that. But I think for this one, you're going to want to keep a more general argument going where we don't necessarily need to pick specific values for them. Okay, that's a good question. Okay, so I just opened up 3 rooms. So let's focus on question 6 first. And then if you guys make some progress with that and you want to start thinking about 7, that's great. Okay, so based on the groups that I checked in, they both those groups did it with cases. I don't know, the group that was working with Lindsay, was that a similar approach? Okay, so I think that went pretty well. Let me just kind of screen share things. Yeah, and so kind of it makes sense to think about, there are 2 ways X and Y can have the same parity. Either they're both even or they're both odd. And in fact, the proofs follow a little bit differently depending on which of those 2 cases you're in. That's right. So I really can't do it all in one shot. And by breaking it up into cases, it's actually a nice way to for a reader to follow what you're doing. And so I'll just kind of, I can fill in the details so the solutions are more complete. But kind of the gist here was, if you assume that X and Y are both even, you got to some point where you show that this thing is actually even, right, as well. So that all 3 have the same parity, that's a contradiction. And on the other hand, if they are both odd, then you probably get to the point where this product you could show is odd. That also is a contradiction. So that was the gist of that one. Were there any questions as far as how those details got filled in, or why this is actually accomplishing the goal of proving this thing by contradiction? Okay. If not, I thought we can at least start a blueprint for this last one. If you haven't gotten a chance to talk about it too much, I don't think, I don't know how far you got into this, probably not too far. So here's an if and only if statement. So again, you know, it might help before you get very far in these proofs to just make sure that you write out, I'm going to have 2 things to prove, right? It's really 2 proofs here. And I've been saying, like, we can, when you're proving things, it sometimes is nice to do this. If you don't like that, I'm just trying to show you, like, there's an alternative. You could do something like this and just kind of explain in words, we're going to prove this by contradiction, which takes up a little bit more ink if you're writing on paper. But in some way, you want to tell the reader, this is what's happening, because if just put yourself in the place of somebody who hasn't had a chance to talk to somebody else, and all you have to do is read their proof, you know, it really helps set things up right away. Like, why is the first sentence of this proof this? So if you tell people how you're proving it, that cleans it up. So you would need to prove each of these things by contradiction. And so this first statement, I'm just going to write the negation of these. So after we kind of say, here's the direction of the proof that I'm going to do, and here's how I'm going to prove it. So those are 2 important bits of information. And so now the next thing that I would expect to see, or somebody else reading this proof, would be, so they're probably going to suppose the negation of this thing over here, which is what we should do. Which would be, let's suppose A minus B is equal to the empty set, and A is not a subset of B. And then at this point, you know, it's, well, how do I get some contradiction? And so I'll just say a hint here would be, you know, if we know that A minus B is equal to the empty set, then try and use that to show that A has to be a subset of B, and that would be a contradiction. And for the second part, similar idea, if we're going to prove that by contradiction, then a good next step would be, okay, well then we're going to suppose here that A is a subset of B, and A minus B is not equal to the empty set. And then I might suggest, you know, starting from this and then trying to show that, hey, look, therefore their you know, their difference must be the empty set. And I think proving each of those things shouldn't require more than 1 or 2 sentences. So I think each of those should be pretty, you should be able to do those pretty concisely. Okay, so just so you guys know the plan, we're not going to learn any additional proof techniques prior to our first exam, which is a couple weeks out. So we're going to really just be focusing on direct proof, contrapositive, contradiction, in looking at some other math realms where we can prove things like with functions. And then after this first exam, we'll kind of move on and focus on another proof technique called induction. And then that will be like all of our proof techniques. Yeah. So for Monday's class, we'll start looking at some material on functions, and we'll come back to that material towards the end of classes as well. Otherwise, yeah, good luck with your homeworks. If you have questions, I've got office hours tomorrow from 10:30 to 11:30. Otherwise, I'll see you on, have a nice weekend. I'll see you on Monday.